Hey everyone, and welcome to the Foundry by Forge College. Today's explainer is all about Merkle tree variance and structure. You can kind of think of this as a detailed review of three entirely different engineering blueprints for organizing massive data warehouses, just, without the headache of actual construction dust. We're going to literally look under the hood of some of the most critical structures in Web3 to see exactly how they tick. Now, if you remember our previous lesson, consolidation and synthesis, we realized something absolutely massive. We saw that the way we handle canonical ordering and empty nodes directly dictates the size and speed of our proofs. You can't just throw data into a tree and expect it to be perfectly efficient. The structural choices you make at the very beginning completely change how big your proofs end up being, and whether or not a verifier can deterministically recreate that root hash. Okay, here's our schematic table of contents for today. 1, the blueprint breakdown. 2, the balanced filing cabinet. 3, the addressed shelf system. 4, the compressed roadmap. 5, inclusion versus absence proofs. And 6, trade-offs and takeaways. Let's dive right in. Section 1, the blueprint breakdown, core architecture. To really grasp our core problem here, we have to understand that the way a variant encodes its keys and handles its empty space basically changes everything for the verifier on the other end. And this brings us to a massive, absolutely crucial rule. Principle 1. Key-to-leaf mapping is decisive. Your mapping choices, like whether you're organizing by strict position or by a deterministic hash path, will absolutely dictate whether your proofs depend on insertion order. It's kind of like the difference between filing a document based on the exact time it arrived versus filing it based on exactly what its name is. Moving on to Section 2. The balanced filing cabinet, also known as the binary Merkle tree. We are talking, of course, about the classic binary Merkle tree. I want you to imagine a perfectly balanced filing cabinet. Every single internal node, or drawer if you will, is the symmetric hash of two child labels right beneath it. Everything is mapped entirely by fixed positions. Left versus right positioning is incredibly meaningful here, meaning it requires strict symmetrical stacking. So let's walk through exactly how verification works here. Step 1, you start at your leaf. Step 2, you combine it with its sibling hash. Step 3, you recompute the parent hash all the way up to the root. You're literally just moving up the cabinet drawers left to right, combining positional sibling hashes until you hit the very top. It's elegant, it's simple, and it's highly symmetrical. Honestly, it's an accountant's dream. Which leads us to Section 3, the addressed shelf system, or the sparse Merkle tree. But what if you have a massive data set that isn't perfectly dense? That brings us to this next architectural blueprint. The scale of this thing is kind of wild. A sparse Merkle tree is like an infinite wall of addressed shelves. It's like building a filing cabinet that reaches all the way to the moon, but leaving like 99% of the drawers completely empty. To make that actually work in practice, those empty spaces collapse into predefined default hashes. We just use a universal standard rule for the empty ones. Looking at the specs here, keys map to fixed 256-bit addresses. This gives us deterministic key encoding, so every single key has a predetermined, fixed home on that infinite wall. And because of that, long stretches of absolute emptiness simply compress down to default labels. This model brilliantly trades a massive logical size for highly deterministic addressing and incredibly compact default rules. Next up, Section 4, the compressed roadmap, focusing on the Merkle-Patricia tree. Okay, I want you to think of a Merkle-Patricia tree like a giant city roadmap. Imagine a long, straight highway segment with absolutely no turnoffs. Instead of storing data for every single intersection along that highway, the tree compresses that entire long segment into a single named road just to reduce the overall depth of the tree. Keys here are paths of hex nibbles, and think of a nibble as just a tiny chunk of data, literally half a byte. And when keys share long identical prefixes, they just share the road to save massive amounts of space. But, there's always a catch, right? Path compression saves a ton of space, but it demands exact metadata decoding. It is amazingly efficient for state storage, but the verifier has to work a whole lot harder. They have to unpack and decode those compressed paths to actually prove they're valid. So you save a bunch on storage, but you definitely pay for it in computational effort. All right, Section 5. Inclusion versus absence proofs. This is the ultimate stress test. So we have our three blueprints. Now let's see how they handle proving a key exists, an inclusion proof, versus proving it does not exist, an absence or non-inclusion proof. Let's pit these against each other, starting with our binary filing cabinet. A binary inclusion proof is easy, for sure. You just show the sibling chain up to the root. But a binary non-inclusion proof? Oh, it struggles. Because positions are strictly fixed, you can't just say, hey, it's not here. You have to explicitly show a bulky, empty leaf value and a whole sibling chain just to prove a whole lot of nothing. Really not very efficient. Now check out the sparse Merkle tree in comparison. Sparse trees absolutely excel at non-inclusion proofs. Proving absence here is a total breeze because you just point to a default empty shelf branch. Or, and this is the real genius part, you point to a neighboring occupied leaf to show that the specific address space you're looking for is definitively empty. It leverages those default rules beautifully. And what about the Merkle-Patricia trie? Well, it handles absence elegantly in its own unique way. You simply show the exact node where the roadmap diverges or where it terminates unexpectedly. You're basically just showing the verifier the street sign where the path for that key mathematically couldn't possibly exist. Finally, Section 6, trade-offs and takeaways on these architectural decisions. As you'll see in some of our other Forge College courses, we actually explore these data structures in live code, which is super fun. But before you write a single line of code, we really need a final synthesis of these trade-offs. So here's the master schematic table putting it all together. This summarizes exactly when an architect should choose each variant. If you've got batch-ordered datasets, use a binary tree. It handles positional indexing extremely well. If you're building key-value registries and you know you need to prove absence frequently, the sparse tree with its implicit default hashes is your best friend. And if you're handling account storage and state tries, where keys share a ton of prefixes, the Patricia trie with its path compression is definitely the tool for the job. I really want this next thought to stick with you. The same phrase, Merkle proof, in different specs can hide very, very different verification steps and metadata requirements. Understanding these underlying structural differences is exactly what prevents you from blindly guessing when you're reading protocol specifications. You absolutely have to know which blueprint you're actually looking at. And that leaves us with a pretty fascinating question for our next module. How do we compute the exact worst-case proof sizes to minimize bandwidth? We are going to tackle that head-on in efficient Merkle proofs and optimizations. Until then, I highly encourage you to visit forge.college to continue your learning and explore way more Web3 concepts. There is a whole world of architectural blueprints waiting for you over there. Thanks so much for joining me on this explainer, and I'll catch you in the next one.